My name is Mark Little. I'm the CTO of JBoss. Hopefully you've heard of JBoss, which is the middleware division of Red Hat. In the next 45 minutes or so, I'm going to talk about a few challenges in the area of dependability that I see for Java middleware in the coming years. So the aim of this talk is to try and give you an idea of where research and development is or should be heading over the next few years, and hopefully by the end you'll see that there is quite a lot of work into these challenges going on elsewhere. Some of it is happening in the Java communities, but quite a bit of it is happening outside, and I hope that after this talk you'll be encouraged to look at what's going on elsewhere, if you agree that these are dependability issues, and maybe try and drive some of this into Java middleware, because I think that it's really important if Java, the JVM, and enterprise Java are to continue to be as relevant as they are today in some of these new areas, then we need to address these issues. I'm going to give a brief history of enterprise middleware just to kind of set the context. Hopefully most of it will be known to many people in the room, but it's useful to at least understand where Java has come from and the components in your typical E6 stack, how they've been influenced over the last 40-odd years. And again, by the end, I hope to show that it actually it's a really good time to be a Java developer. I can't think of any period apart from when Java and subsequently J2E were first created when it's probably as good a time to be a Java developer. There's despite the fact that I think there are a number of dependability challenges, that means that there are these areas that if you're really interested in doing some groundbreaking work, then there are these areas, and they're open for good developers and good open source, hopefully, contributions. And like I say, hopefully go out and fix these problems, and then maybe in a few years' time I'll be sat in the audience listening to one or two of you talking about how you've solved the things that I'm about to discuss. So, enterprise middleware didn't just spring into existence when Java or J2E came on the scene. It's been around in one way or another for well over 40 years. RPC, for instance, dates back to the 1970s. Obviously, what people in the 70s considered to be enterprise middleware was significantly different to what we consider to be today. But middleware has evolved. It continues to evolve with each new wave. It builds on what has gone before, throwing out some things that may no longer be relevant, updating things that are that need to be changed. And if you look at your typical E6 stack, you can see influences by one or more of the things that I've written on this slide. Even web services, whether you like it or not, has influenced E6. REST, Corba. Corba was the middleware platform of choice in the mid-'80s and early '90s. DCE, which predates Corba. And then in the Microsoft world, you have COM, DCOM, and .NET. And going back even before some of these things, there's lots of work on bespoke middleware platforms, such as Argus and Emerald and the like. All of these have influenced their successors, and the ultimate successor, at least in our world, is E6. If you look at a typical E6 stack, whether it's a Glassfish or an AS7, you can see we have RPC and message passing. Like I said, RPC dates back to the 70s, message passing to even before that. Distributed objects. So I mentioned Corba before. Corba was probably certainly the first standard distributed object stack out there that popularized object-oriented programming. All of these frameworks and stacks in one way or another had a focus on reliability. When you're developing in a distributed environment, having reliability and having fault tolerance, whether it's through things like transactions or replication, is extremely important, because the failures of a component in a distributed environment can take down your application that's running elsewhere. So having an ability to often mask and certainly tolerate failures in one way or another is very, very important, and is a kind of a common thread through most, if not all, of the successes of EE6. So, given all that, somebody certainly from the outside looking in could ask, well, surely we're done. We've got everything we need. Many of you in the audience are hopefully developers of complex real-world applications written in Java or some other language. You'll know as a result, today we can definitely do reliable inter-process communication. We can maintain distributed state, coherent distributed state, consistent distributed state across multiple instances in the presence of potentially an arbitrary number of failures. We can detect or suspect errors and failures and try and mask them and recover from them. We can have secure interactions. All of these things, for instance, have helped to turn the web from the original document server that Tim Berners-Lee thought about to the backbone of e-commerce today. So, as I said, surely with all the things that we've done over the last 40 years in EE6, we're done. That's it. We can all kind of kick back, do something else, become farmers or whatever else takes your fancy, and let the world just build on everything that we've done. Well, unfortunately, the times have changed over the last few years, and certainly over the last decade. And that's going to influence where we need to go in the future with our middleware stacks. So just to give you an indication of what I mean by that, well, here we have a 68040. Can I have a show of hands of who actually remembers, let alone used a 68000? Not necessarily a 68040, but 3. Okay, now I feel even older than I did when I entered the room. So 68040 was like the processor of choice. About 20 years ago, it ran, desktops. It was it was basically like your i7 is today. It was the thing everybody aspired to have. It pushed the envelope. It was very, very fast. Let me put it that way. Well, on the further down on that screen on the left-hand side, there's a 16-bit microcontroller. You can see that it's roughly the eighth the size of a penny. This is from 5 years ago, and it has more processing power than that 68040 from the 1990s. And that's 5 years ago. So you can only imagine the equivalent today is orders of magnitude more powerful, has more memory on it than you probably have on your laptop of a decade ago. Here's a graph that I dug out from that somebody did from 2010 that showed the performance of various processors that were running in mobile devices back then. So pretty much first generation smartphones compared with the Pentium 3. Hands up anybody who's used a Pentium 3? Oh, more. Great. Okay. So you can see that 2 years ago, with the exception of floating point, which you can pretty much understand, you've got your Nexus 1, your Snapdragon processor at the bottom that is beating a Pentium 3 certainly on integers. And again, that's 2 years ago. So fast forward to today, when we had the iPhone 5 with an A6 processor. I've got a Galaxy Tab laptop, pad that's got a quad-core processor in it. Pentium 3, which again was, the thing that was powering laptops of 10, 12 years ago and was considered to be, the fastest of its time. Definitely faster than that now. A lot faster than that. And if you look around at the world that we live in today, and look around at what probably you've got on your laptop, in your on your lap, in your pockets, maybe at home, these processors that are in mobile devices are typically also in cars, in iPods, in cameras. These things are what some people of 30 years ago would have considered to be a supercomputer, and certainly of 60 or 70 years ago, people wouldn't even have imagined that we could ever need, let alone be able to develop. All of this has a significant impact on middleware. Middleware for the next decade is going to have to evolve and take into account the differences in the deployment environments and the characteristics of these devices, just as middleware 10 years or so ago had to evolve to the evolving Pentium 3s and Pentium 4s and multi-processor, not multi-core, but the small number of multi-processor boxes that were out there. So what this means is that there are a number of problems that we haven't really had to tackle up to this point because the environments that we've been developing for could really be classed as last generation, if you like. If we're thinking about the next generation as this ubiquitous computing, as I said, they pose completely new, some new challenges that we haven't had to contend with to this point. And I've categorized these in the following 4 things, which we'll cover in the rest of this talk. So they're coordination and consensus, multi-tenancy, which is not just for cloud, large-scale data storage and access, and governance and accountability. So what do I mean about coordination and consensus? Well, consensus and consensus protocols have been around in human history for thousands of years and used in computing for a lot less time, maybe 40 years or so. If you've used transactions for instance, in a database, whether it's an Oracle or MySQL or DB2, for instance, then you may have come across transactions. And I'm going to use transactions simply as an example. There are other areas where consensus protocols are used. But a consensus protocol, fairly obviously, is used to ensure that multiple parties within some activity agree on the outcome of that activity. And in a transaction system, we have a designated coordinator whose role it is to ensure that the parties come to this consensus using a protocol. The typical one that's used is what's known as two-phase commit. There are other ones. Three-phase commit is another example, but it's not that commonly used. Consensus protocols today are typically based on a central coordinator, where you have this designated party whose role it is to run the protocol amongst the participants and to ensure that they all agree to the outcome. So in a transaction system, the coordinator will ensure that all the participants agree to either commit the transaction or roll it back. We have no participants that go one way and others that go the other. That would not be consensus. And consensus protocols today run with RPCs, typically RPCs, that have guaranteed termination protocols built in. So there's no way in which a consensus protocol can just arbitrarily continue until the heat death of the universe, for instance. Now, as I said, typically they have a coordinator, a single coordinator, but in a distributed case, you may have a tree of coordinators, which is what I've got in the diagram here. It's pretty much the same thing. I only mention it here to show that there are protocols that span multiple coordinators, but ultimately the outcome is the same. The root coordinator, the red circle here, is controlling the consensus down the tree with the blue coordinates that are the proxy coordinators and the squares, which are the real participants. But the protocol, two-phase commit, for instance, runs across all of these participants, the subordinates and the square boxes, driven from the top. And it's synchronous, and everything, even in the presence of failures, in a transaction system, everything will agree on the outcome of the transaction, as in to commit or roll back, because it's all driven by the coordinator. There's a lot of work that the coordinator has to do for failures, such as logging, for instance, but the protocol will ensure that even in the presence of failures, we have a guaranteed consistent outcome. That works fine if you control the environment, and typically if you have a small number of participants that don't span a large number of network hops. But What about the kind of environment that I mentioned before, the ubiquitous computing, where we've got processors, mobile devices? Let's just think about mobile devices, for instance. In this kind of environment, it's extremely loosely coupled, and the parties are autonomous. They're peers. There really is no way in which we can have a centralized coordinator or even a tree of coordinators. That doesn't scale. It creates a bottleneck, and in the presence of failures, then it also causes a lot of problems in actually getting a resolution. In an autonomous peer-to-peer network of mobile phones, the network can go down at arbitrary points. Just try using the network here, or try using Oracle's Wi-Fi. It's not exactly the most reliable. You might want to switch off your phone, and you will still, as an application developer, you'll still want the application to resolve in a consistent manner. In this kind of environment, as I said, we don't really have the ability to designate a single participant as a coordinator to drive the outcome of the protocol. We have multi-party interactions. It's asynchronous, and that means it's often truly asynchronous, not just a thread that's running an RPC that will then eventually join. A truly asynchronous fire and forget environment is one in which there is no guaranteed termination period. The message goes out, and just because you haven't got a message back, a response back, doesn't mean to say that you've had a failure. It just means you haven't had a response back yet. That kind of environment you need to take into account network latencies and other things in order to develop a protocol that can still terminate, and still terminate with a consistent outcome that the application can then use. In this environment, we tend to need to have the parties being able to control their own outcome, their own destiny. Each of them needs to essentially be at the same level as any other party in this activity. They all need to be able to make unilateral decisions about their own outcome based on their current state and the messages that they have seen, and maybe the small number of participants that they know are involved in the activity, but without having to get global consensus, which is what happens with a coordinator. So here's a quick pictorial representation of what I said. It's a typical one. If you've used Amazon, then this is exactly an Amazon. You've got a buyer, you've got a seller who is Amazon, you've got a shipper. There's no need for a central coordinator here. Each of these participants, the buyer, the seller, the shipper, is its own entity and wants to control the interaction as it sees it. I could, or you could, model this using two-phase commit. You could model it using a traditional centralized coordinator protocol. However, as I mentioned before, there would be significant issues in terms of reliability and fault tolerance. It really doesn't make sense, particularly when, as you can see down the right-hand side, when the time between message exchanges could be measured in hours and days. Again, certainly transactions, but traditional consensus protocols tend to fail or tend to work less efficiently when you're talking about hours, days, weeks, or months in between message exchanges. So what we need to see in terms of improvements to Java and Java Enterprise Middleware are new conversation message abstractions, basically, that allow for coordinating of these peer-to-peer interactions without a centralized coordinator, but that allow for multilateral termination guarantees that give guarantees to the application so that it can reason about the state in which the conversation is terminated. There are a number of loosely coupled protocols and efforts that have been going on in the industry for a number of years. As I mentioned at the start, some of the work that we're going to talk about in the next few slides has been happening in the Java world. A lot of it has been happening outside. Some of the work that we have been doing in the industry around loosely coupled interactions has been happening in web services and REST, because web services has at one point or another been the backbone of SOA, and service-oriented architecture has always had loose coupling as its main reason for existence. And if you look at some of the web services transactions standards that have been done in Oasis, there's one called business activity, which is specifically about this kind of interaction. It's not about using two-phase commit, it's about having loosely coupled interactions where the parties are in control of their own destiny. There's also work going on in the REST environment with something called REST compensation, which is basically very, very similar to business activity, just modeled in terms of resources. But probably the two most interesting areas to look at are Rosetta Net and EBXML. Has anybody heard of Rosetta Net or EBXML? 2. Okay. 3. All right. There was a JSR around some of the work that was going on in Rosetta Net, 157, that got withdrawn. I know that some Java middleware products, and I will mention in competitors, Oracle, has some work in the Rosetta Net space. So despite the fact that there aren't any standards here, certainly in the Java space, there are products that push Rosetta Net. If I go back, this down here on the right-hand side is from Rosetta Net. So you can model these kind of conversations in some enterprise middleware stacks in Java, but not in all. And I'm hoping that that we'll see a lot more of this coming in the future. Whether there'll be a new JSR around Rosetta Net or some of the stuff that's going on or went on in EBXML, I don't know. But what I hope we don't do is reinvent the wheel. Despite the fact that, correctly, I think some people can say, oh, well, EBXML was a little bit too heavyweight, which it kind of was. There are some really good things in EBXML and in Rosetta Net that I think we should learn from without having to reinvent the eponymous wheel, as we often seem to do in software engineering. So the next area that we really need to see improvements in, certainly for Java, is on multi-tenancy. Now, as I said at the start, it's not just for cloud, but I'll focus on cloud just for now. So hopefully most people here have heard about cloud enough over the last few years at Java 1 and at other events to understand what I mean by platform as a service. But in order for platform as a service to deliver on its benefits, which is, you don't have to fork out for your hardware for it to sit idle for 80% of the time. You pay for what you need when you need it. We need to have high density of applications. It may be cheap for you as a user of platform as a service, but as a provider of a PaaS who's building it on an infrastructure, whether you're an Amazon or a Red Hat or an Oracle, it's not zero cost. You still have to buy these machines. You still have to house them somewhere. So what you really want to do is cram as many applications onto a device as possible, and ideally as many applications onto a single VM image as possible. Unfortunately, typically Java middleware stacks haven't been architected with multi-tenancy multi-tenancy in mind, and I don't mean just solving the class loader issue. Class loading is a problem, but it's not the only problem with multi-tenancy. What this means is that in order to ensure that we have failure containment so that a rogue thread on an application that may be running completely independently on a JVM from other applications that are running on the same JVM, in order to prevent that rogue thread bringing down the whole JVM, we tend to run a single user's apps in a single JVM and have a single JVM per virtual machine. And that really doesn't scale. So the JVM, hopefully nobody in this room disagrees that the JVM is here to stay. Whether it's Java or not that's running on it, I think that's irrespective. The JVM is a great piece of software. If we were to re-implement it from scratch, we're probably looking at hundreds of man-years. And it's not just the JVM itself or the languages that run on it. It's the ecosystem that's built up over the last 10 plus years with editors, with Maven, with all the other associated things that we take for granted. So one way or another, I think the JVM, it's future-proof. But there are only really two ways of solving this multi-tenancy problem. One is to make the JVM so small and so lightweight that you can run one app per JVM and not worry about it. And that's kind of the Dalvik route. So if you've got an Android phone, each of your apps is running on essentially its own JVM. So if an app crashes, it's not going to take down the whole phone. Although, for some reason, my HTC did crash on the way down here, so I need to figure out what was going on there. But ultimately, it shouldn't be crashing the whole phone if an app goes down. The other way is to remember some of the things that we probably or some of us may have learned in operating system classes, and make the JVM much more like an operating system, so that you can run multiple processes per JVM and have them red zone protected. What I mean by that is that on your operating system, if it's a mature operating system, then if a process crashes, it's not going to take down the whole operating system. These days, you very rarely have to reboot your machine if a process goes awry. If you're running something like Fedora and you fire up a terminal and you kill -9 a process, you would not expect the whole machine to die. That's because all of the processes are red zone protected. So we can have isolation and independent failures. That's the kind of thing that we need in the JVM. We also need to be able to have more real-time capabilities and have deterministic scheduling and garbage collection. There's quite a bit of research going on in this area. Unfortunately, some of it has been pushed out. So there was work going on in SE8, particularly around modularization. If you've been keeping track of that, you'll see that that's now been pushed out of SE8. That's now further out. There was the JVM Language Summit that was held previously to Java 1, and there were some interesting things going on there. And I know that there was some work that BEA and others were doing in this area of a real operating system for the JVM. So there has been work going on in this area. There is work that is still going on in this area, but we certainly need to see a lot more being done in this. And if you're interested in this, go and have a look at what's going on in OpenJDK, because despite the fact that modularization has been pushed out of SE8, I know that the work is still going to happen in OpenJDK, so that we can at least get this into the open source community and people can start playing with it and giving feedback. So the next big issue is what we can broadly call large-scale data access. So relational databases are great generalists. They've been around for 30 or 40 years. Most of them today, even in open source, support ACID transactions. They support strong consistency, and you can replicate them. So you no longer have to worry about a single point of failure. You can have multiple copies of your database running on typically the same local area network, and they'll be strongly consistent. But they weren't really designed for large-scale data. And by large-scale, I'm not talking about hundreds of gigabytes or maybe even a terabyte. I'm talking about petabytes and beyond. And also by large-scale, it's not just the quantity, it's the distributedness of it. So the scale, how far apart the data is, also plays a real role in what I mean by large-scale data access. These issues have resulted over the last couple of years in a NoSQL and a NewSQL effort. Probably most of you have heard of NoSQL. You may not have heard of NewSQL. It's a term that was coined by the 451 group about 18 months or so ago. Basically, some of the original developers of RDBMSs believe that there's nothing actually inherently wrong with RDBMS as far as scale is concerned, in terms of the principle, but the way in which they were implemented 30 years ago, they've implemented bottlenecks. So they've gone back and they've looked at RDBMSs and they've re-implemented them from the bottom up, and this has resulted in something called NewSQL, which they believe they're kind of true in-memory relational databases. They don't hit the disk at all, and they believe that they offer a better solution to a lot of the problems that we're seeing than NoSQL. Just to give you an idea of what I mean by large data, though, in the last 5 years, we've seen a 10-fold growth in data. The end of this year, the amount of information that is stored on the internet will top 3 zettabytes. If you were to write that information to DVDs, you would be able to create a tower of DVDs from here to Mars. It's that phenomenal amount of information. Much of that data has, these days, either a location or a timestamp, and therefore most of it is coming from sensors or mobile applications. The kind of queries that we're now seeing people do on this data are very spatial or time dimension aware, which again is not necessarily something that your traditional relational database is very good at. So this led to, as I said, the NoSQL movement, and there's quite a lot of NoSQL efforts around. There's a number of categories. There's tuple space, there's column, there's document, and there's graph-based. Typically, they go for a kind of a weak consistency replication approach, where it's as you scale things up and you have your replicas, for want of a better term, on different machines that are physically remote from each other. They may not be strongly consistent. There may be some level of inconsistency between these replicas. If the replicas are close by, you may have domains of strong consistency. So if you're running a number of cached copies, for instance, on a local area network, then the implementation may guarantee that they are strongly consistent. But as you move out of your local area network, they may have a level of inconsistency. Typically, in order to maintain consistency, whether it's how inconsistent, whether it's consistent or inconsistent, they use a gossip protocol. So you don't have a protocol where suddenly I will tell everybody to stop the world, here's the latest update of the state, and now everybody moves on from there. I might tell somebody else what my state is, and then he tells somebody else, and then that person tells two other people, etc., etc. And in fact, in some protocols, no one member of this NoSQL group will know about every other member of the NoSQL group. Gossip protocols have been around for a number of decades, by the way, and they're very good for disseminating updates in the presence of failures, but there's typically no bound on when the updates will have fully propagated. One of the downsides of NoSQL is that there's a thing called CAP theorem. I'll do it again. Hands up who's heard of CAP, consistency, availability, and partitioning. Okay, so CAP theorem basically says in any environment, you can only ever have two of consistency, availability, and partitioning. So consistency and availability, you can't tolerate partitions. Consistency and partitioning, you don't have availability. What many of these NoSQL solutions have gone and done is they've ignored transactions, because distributed transactions are typically a strongly consistent protocol. And strong consistency and CAP don't go hand in hand. So in some cases, ignoring transactions because of CAP makes perfect sense. However, in some implementations, they cite CAP more as an excuse rather than as a good reason. One of the other knock-on side effects of weak consistency, though, is that it's weakly consistent. It can be much more difficult for developers to actually understand. When I do a read, I'm not actually necessarily reading the real state. That state may be updated a millisecond after I've read it, and I won't necessarily know about it. So it becomes more complicated for developers who've lived in this strongly consistent world for 30 or 40 years. And also your requirements may change over time. So your application's requirement on consistency may move over time from strongly consistent to completely inconsistent and back again. So a bit like I said for the JVMs, I don't think relational databases and SQL are going to go away. They're a fact of life. They're very, very good generalists, and most implementations, most deployers I've seen who are using NoSQL are using it to augment relational databases. I think we are actually starting to see a lot of the NoSQL vendors who had given up on transactions now coming back to transactions and looking at what are known as extended transactions in the NoSQL space. So an extended transaction is where you can relax in a controlled way some of the ACID properties. And again, the business activity spec that I mentioned earlier in web services is an example of an extended transaction. And in fact, some NoSQL implementations have moved to say we will support strong consistency as the default with full ACID semantics. But I think we'll see a lot of exploration certainly in open source and in the research community between trading off strong and weak consistency, what it means for application developers, what it means for the underlying implementation. And these days, memory is the new primary store. It's very, very easy to just ramp up 16, 32 gig of memory. It's very, very easy to just have a heap size so big that you really, for a lot of the data that you're doing, you don't need to ever think about disk. That has an impact on applications. It also has an impact on frameworks and some implementations that have been implemented with the assumption that disk is always going to be a certain level of speed compared to the application. Transaction systems, for instance, I keep coming back to transactions, but again, it's just as an example. Transaction systems have been implemented over the years using a log to record where the transaction is as it progresses, so that if there's a crash we can recover and continue the transaction. The disk is typically where the log is written, and the disk is slow compared to main memory. The disk is often slow compared to the network. So transaction systems over the last four decades, their implementations have spent a lot of time optimizing the log, making it typically like append only, write once and maybe, write many and read once during recovery. A lot of effort has gone into that. If you take the disk away and say that you don't ever have to hit disk and you only ever have to hit memory, and memory is so reliable and so fast, then maybe you don't have to spend so much time on the log. Maybe the log implementation is needs to be no longer so complex, and there are other trade-offs, other areas of the transaction environment that you now need to optimize. There's a lot of effort going on in NoSQL in the JSR. Well, I say a lot. There's two efforts. There's JSR 107, which is caching, and there's JSR 347, which is data grids. I expect I had hoped in the E7 timeframe, but that's not going to happen. So it's going to be E8 to see more NoSQL standards making their way into the JCP. I still expect to see that, but like I said, I think it's going to be E8. It's very, very important that we do this, as in push more JSRs in this area, because at this point, people talk about NoSQL as though it's like SQL, as though there is a standard. There is no SQL standard for NoSQL. Even amongst tuple space vendors or graph-based vendors, there is no standard. It's very easy to get locked into one NoSQL implementation and not be able to move off. I would really like us to see a lot more effort going into standardizing some of these things. So the fourth issue is governance and accountability. So if you think managing a local environment is hard enough, well, obviously think about what it means to manage a distributed system. It's an environment where you may not even control the whole infrastructure. You may not have access to the whole infrastructure to monitor it. You may have to work with your peers in other organizations. And the failures that can happen in a distributed environment are much, much wider. You can have the failure of a component that takes down another component in a completely different area of the network. You can have network partitions that eventually heal or that never heal. You could have participants. Just because participant A can talk to participant B doesn't mean to say that participant B can talk to participant A, for instance. Large-scale distributed systems are even more complicated to manage. I would not want to manage the web, for instance. It would be impossible. If you look back at the ubiquitous computing slide that I showed at the start, just think about trying to monitor and manage all of that. It, again, is going to be almost impossible. And then we start to move into the areas of trust. If you don't control the infrastructure, it becomes even more difficult to trust it. And as a user, if you're using your back office system in your VPN, hopefully you trust what your IT people give you, that it will work and that they're not going to leak your details to somebody outside of the VPN. But if you're using somebody else's system that you don't know, in fact you don't even know who they are, why should you trust them? Governance becomes extremely critical in this kind of area. Governance and trust. You need to ensure that you know what services are running, what service level agreements are up and running on each of these services, and have something that monitors these service level agreements and lets you know when they are violated or even if they are about to get violated. So cloud, and the same can be said for mobile, but cloud raises some very important issues of trust, particularly around storage. There are legal implications of using third-party components in certain countries as well. One of the reasons I think that private cloud is probably going to be far more important than public cloud is that hopefully private cloud, if you're using your back office system, you will not have the trust issues that you will have with public cloud. Despite the fact that a lot of people are storing things on public clouds, for instance, Amazon, if you read the small print that an Amazon gives you, all bets are off. When the Amazon outage happened a few weeks back and then the one that happened a year or so back, the small print basically says, sorry, you can't sue us, and, if we leak your data, sorry, but again, you can't sue us. So trust is something that needs to improve significantly in cloud, certainly in public cloud. In the area of trust, there's also an area of accountability. If I say I'm going to do something to you and you agree with me that you want me to do it, later on, if you find out that I didn't do it, it can be important in a legal situation for you to be able to prove that I said that I would do it and that you enacted on that. That's accountability. Again, in cloud, both public and private at this point, we are missing strong accountability. So ideally what we should have for cloud is this notion of a flight recorder, a black box. Now, I'll kind of skip to the last bullet here because all of what goes before is kind of summarized in that. There's a component, a hardware component called a trusted platform module. Anybody heard of a trusted platform module? Okay. If you want, or I would encourage you to go and look up TPM, Trusted Platform Module. Basically, if you have a machine that has a TPM on it, that Trusted Platform Module maintains information about everything that happens on that machine in a non-reputable, accountable manner. In fact, in a way that can be used in a court of law. Something like that for the cloud is critical for the cloud to really succeed for big businesses. For any business, whether it's a bank or a healthcare system, to want to move its data to the public cloud, you'll have to have something like this. And at this point, there really is very little research going on in this in software. It's all been happening in hardware. And there's not a lot of hardware that has TPMs. There's a hell of a lot more, pardon my French, there's a lot more cloud hardware out there that does not have TPMs in it than has TPMs. So a software version of a trusted platform module, I think, is critical for cloud, for as I said, for the success of cloud. So the next decade, I think, certainly of Java middleware, has got to be defined by ubiquitous computing. Enterprise capabilities are a necessity. The types of apps that we think we're running today on our mobile devices and pads, they may be games, but they're really not going to be games for very much longer. In fact, if you look at what's going on with the Department of Defense giving smartphones to every one of the Army guys, healthcare environments, probably in the US, but certainly in the UK, giving pads to doctors and nurses so they can access patient data across the network and putting RFID chips on drugs. The applications that are running on these devices are growing in complexity and require enterprise middleware capabilities. Java should play a leading role in this. The JVM should play a leading role in this. There are issues that need to be resolved in the JVM and in enterprise Java middleware in order for us to ensure that we can play that leading role. Because, one way or another, whether we do something with JVM and Java and E7 and E8 or not, these problems aren't going to go away, and somebody else somewhere is going to solve them. I would like it to be on the JVM with Java or with a non-Java language running on the JVM. And as I said at the start, I think it's a very, very rich area of research and development for the next decade, and hopefully some of you will want to get involved in it and push the standards. And before I open it up for questions, if there are any, I just leave you with this quote from Richard Hamming, who gave the speech when he accepted the 1968 Turing Award. And basically you can summarize it as not invented here syndrome. So anybody got any questions? No questions? Yes. So I say that because certainly for two reasons. The first is I've been saying it for the last 3 years, and it kind of just comes out because I really do believe it. I think that the trust issue, the security issue, the fault tolerance issue, those are big problems with public cloud. and hopefully they've been solved by your IT department. We all complain about IT. I complain about IT. I can never get a mailing list created in less than 2 weeks. But the infrastructures that they put up typically are pretty good. And if they crash, I can lift a phone and I can shout down the phone at somebody and they'll fix it. I don't have a direct line to Amazon for them to fix it. The second reason is, certainly when we've been talking to our customers, we're getting a lot more drive from customers on private cloud than on public for these reasons as well. But they've gone and invested. They've spent millions of dollars on back office systems, and they want to keep using them. They want to use public cloud for cloud bursting, and in which case they need the security and the fault tolerance issues to be resolved. But 90% of the time they're going to be using cloud on the back office, on their existing infrastructures. Oh, sorry. Well, Red Hat. I mean that. Because an awful lot of people are running, Linux in one way or another, Fedora, RHEL, CentOS. Like it or not, probably Microsoft, and it's usually not. And it'll be the usual suspects, like an IBM, and I would say HP, but not these days. So probably IBM, Microsoft, Red Hat, maybe SAP, if they can get their act together. Some of the public cloud vendors like Google and Amazon, I suspect they'll try and move into the back end. I don't know how successful they'll be. I wouldn't discount them though. Any other questions? Because, well, I think that the future is ours to lose. I don't say that as a kind of a glib statement. I think if you look at Dalvik, it's kind of Java. It's not really Java, but it's kind of Java. And a lot of the cloud platform as a service that's out there, if the platform as a service vendor didn't come out with Java to start with, they've followed up with it pretty quickly afterwards. If you look at a lot of new languages that have come out, I've been in the industry for the best part of 30 years, and I've seen lots of languages come and go, and I've seen lots of explosions of languages, but I've never seen as big an explosion of languages as I have in the last 3 or 4 years. We've got a huge number of languages. I counted the number of, because I'm doing a different talk, but the number of languages running on the JVM it's like 18 plus. Things like Ada, for God's sakes. Who wants to run Ada on a JVM? But apparently some people do. And people who come up with new languages, they either target the JVM first or they port to the JVM pretty quickly after that. The JVM is the place to be. So like I said, I think it's the future, whether it's running on pads, mobile devices, sensors, laptops, desktops, in the cloud, it's Java based. It has to be. Or we've really fumbled the ball. But we could fumble the ball by not addressing one or more of these issues that I put here. Like, for instance, think the multi-tenancy one. If we don't address the multi-tenancy issue, it's going to become much, much harder for us in some areas. Any other questions? Okay, thank you very much for coming.